Good afternoon. So I've decided there's something I really miss about teaching from home and not teaching from school that I would not have thought about. I miss the really good air conditioning at school.
That's fair.
We have 17-foot vaulted ceilings in our apartment, and there's a skylight. And so I built an insulated curtain to put in that skylight, but in order to install it, we had to rent a 10-foot ladder from Home Depot. So that's what I have done in the last week. Oh, that's the wrong chapter. We're not on chapter 17 yet. Let's try that again. And thank you, Aylin. I like this shirt too. I own a lot of science shirts. And I think it's because my friends don't know what else to get me for gifts. And so they buy me nerdy science shirts and they buy me school supplies. My mom buys me like a pack of new school supplies every year at the start of a school year. And I'm not complaining. I enjoy it. Okay. We're going to finish chapter 16 today. Hopefully start chapter 17. You know, I have a couple nerdy science mugs, but they stay at school. Yeah, and I think those have all been gifts from students. I do have a beaker mug. It's on my desk at school as my pencil holder. So we are going to finish chapter 16 today. Hopefully start chapter 17, but we'll see. And then one quick announcement about next week. On Monday, I have a funeral to go to. So we're not going to do live lectures on that day. I'm going to pre-record the lecture and post it. And then I'll also make sure that I'm posting whatever information you need for the lab that day. I will be available through text and email, but I live in Long Beach and the funeral's in Riverside. So, you know, it's going to be an all-day event just because of the drive out there and back. So I will still be available for communication, but I won't be available for a live class. So I will get that posted. I'm hoping to be able to make it on Friday and then get it posted the same day. So it will be available for you. And then I will remind you of that through a Canvas announcement as well. And then when I post the video, I'll remind you too, just so you don't have any confusion on Monday as to why I'm not there. All right, chapter 16. We have talked about the first half of this chapter, which for the most part, the biggest thing was the 1,2 versus 1,4 addition reaction. This slide actually has the rest of the reactions on it. We're going to talk about the first one in quite a bit of detail. So the first one is the cycloaddition, which is reaction number 4. Electrocyclic is reaction number 5. Oh, wait. I'm sorry. I think I started too late. It should be 3 and 4. Number 3, number 4, and then number 5. These are all on the same slide, though, because they all fall under the category of pericyclic reactions. And that tells us a couple things. One, it tells us that the intermediates of the reactions don't have any charges or any radicals. So they don't fit into the categories we've seen before. And then the other thing is that they're all one step. They're all concerted. So what's actually on the screen right there are all of their mechanisms. So they're each a 3-arrow but 1-step mechanism. And then this table that's on the bottom down here is a great representation of what's happening in these reactions. Because they're all concerted, some of them it can be a little bit difficult to see what's actually changing. And so this is telling us how the bonds change. So how the sigma bonds change and how the pi bonds change. And I'll come back to this. I'll reference it as we talk about each one. So we are going to start with reaction number 3. So this is the cycloaddition reaction. And more specifically, it's often referred to as the Diels-Alder reaction, which is the scientist who figured it out. So I'm going to number some carbons. In order to do this reaction, we have to have 2 molecules. The first one is a diene, so a structure with 2 double bonds. And then the second one is a dienophile, so something that likes that diene. There are always going to be 6 carbons involved in this reaction. And I number them the same way every single time. 1, 2, 3, 4, 5, 6. When this mechanism happens, we are going, and honestly, it can go clockwise or counterclockwise. It's concerted, which means that it's all going to happen at once. So because it's a domino effect, we just need to draw that first arrow, and then the rest kind of fall in line. So this is what I mean by that. We're going to form a new sigma bond between carbon 1 and carbon 6. So I'm going to take these pi electrons, and I'm going to draw my arrow right there. Now, normally, I would tell you to not draw an arrow just out into outer space. This is kind of one of those exceptions, though. We're not drawing it to the other sigma bonds or to that pi bond. So it is going a little bit out into outer space, but we do want it close to carbon number 6. Obviously, we can't stop there, though, because if we did, carbon 6 would have 5 bonds. So we're going to break the pi bond between 5 and 6. So I'm going to take those pi electrons, and I'm going to go right here. And that's going to form a new sigma bond between 4 and 5. And then same thing here. We can't stop there because carbon 4 would have 5 bonds. So I'm going to take that last pi bond, and it's going to go right here. So this arrow is making a new sigma bond, this arrow is making a new sigma bond, and this one's making a new pi bond. So every time we do a Diels-Alder reaction, we are going to end up with a 6-membered ring. And between 2 and 3, there will be a double bond. So this pattern is going to happen every time. What's attached to that ring is going to change. So in this case, there was, just a generic X, but it is showing us how things are occurring. In that table, this one tells us that we're going to gain 2 sigma bonds, and we're going to lose, not gain. We're going to gain 2 sigma bonds, and we're going to lose 2 pi bonds. So we gained a sigma bond between 1 and 6, and a sigma bond between 4 and 5, and overall we lost 2 pi bonds. So originally there was 3 pi bonds between those 2 structures, and now there's only 1 pi bond. So the only one we have left is that double bond between carbons 2 and 3. This is a big rearrangement of electrons. The little diagram down here is showing us which bonds are breaking, which bonds are forming. We're going to go through some Regio Selectivity and some Stereoselectivity on this, and then we will do a practice 1 or 2 as we get through it. On that dienophile, so remember the dienophile is just the double bond, so not the diene, but the one with the double bond. The reaction will go faster if there is an electron withdrawing group attached to that dienophile. Now, we haven't talked a whole lot about electron withdrawing groups and electron donating groups, but I'm going to give you a little quick crash course, and it is something we'll actually talk about a lot more when we hit chapter 17 and 18. But an electron withdrawing group, one way to see them is that it's often a pi bond, especially if there's a heteroatom involved. So notice the 4 examples on the slide right here. Those are all carbons with a pi bond to a heteroatom. So we have 3 that contain a carbonyl, and then the CN there is that carbon triple bond. And then an electron donating group, again, there's more than one category for this, but the most common is if there's a lone pair on a heteroatom next to the group we're talking about. So an example, if we had just an alcohol attached, this is considered an electron donating group because we can do this. So it's donating those electrons towards the pi bond, whereas these electron withdrawing groups are doing this. The reason why that electron withdrawing group is going to help speed up the reaction is what we end up with after that resonance occurs is that. And so the hybrid of this structure is going to put a partial positive charge on that end carbon of that chain. And if we look at the mechanism that's up here, this arrow is forming a new bond between the diene and the dienophile. So those electrons are going to be more attracted to the dienophile if there's a partial positive charge there for it to be attracted to. So having that partial charge will help speed things up. The last part on this slide is talking about stereochemistry, and it tells us that the stereochemistry is retained. So notice that this whole slide is just in reference to the dienophile. So the stereochemistry being retained is talking about just the stereochemistry around the dienophile. So what that means is that if it's cis to start with, it will be cis to end with. And if it's trans to start with, it will be trans to end with. So it will keep the same arrangement that it started with. So what about the diene itself? We did the dienophile half. We're going to do the diene now. In order for that mechanism, that domino effect chain reaction to happen, the diene has to be in the S-cis conformation. That S, remember, stands for single bond. So this is the S trans. And this is the S cis. And in a chain formation, there is free rotation around this bond, so they can interconvert, but the trans is going to be more stable than the cis. So in order to do this reaction, it has to rotate into that cis conformation. So if we can lock it into that position, it's going to make the reaction go faster because it doesn't have to change into that position first. So the best way to do that is with a ring. So the example here is a cyclopentadiene. So we often see rings for this reaction because it's in that locked position. So let me do a little bit of numbering on here. 1, 2, 3, 4, 5, 6. And again, I ignored that extra carbon on that ring, that 5th carbon on the ring, because it's not taking part in this Diels-Alder reaction. So I'm just ignoring it. And yes, we have the product drawn right here. This is called a bridged ring because it's a ring with kind of a bridge in the middle. The way it's drawn there definitely works. You can see that we started with a trans dienophile and we have an X pointing up and an X pointing down. So it's still trans. I'm going to show you a different way to draw it though, because drawing those bridge structures can be a little bit tricky. So I'm going to draw just my regular cyclohexane. I'm going to number my carbons the same way I did for all the other ones. 1, 2, 3, 4, 5, 6. And I know that between carbons 2 and 3 are going to be a double bond. So that's my basic Diels-Alder product. And then I just need to fill in the rest of the pieces. So I'm just going to switch colors for the rest of the pieces. On carbons 5 and 6, we have the 2 X substituents, and they're trans. So I'm just going to make one a wedge and one a dash. I could have done it the other way around. It doesn't matter. And notice up here it says plus En plus the enantiomer. So the other one will form as well. So saying plus En is the cheater's way to show both products, the quick and easy way. So the one thing I am missing though is that single carbon that is part of that ring. And so we look at where it's bonded, and the way I have it numbered is that it's between carbons 1 and 4. So on my green structure down here, that's how I'm going to draw it. There it is. So it's definitely not the prettiest way to draw it, but in my many years of experience, I've definitely found that students are able to draw that way easier, and they're just able to see it easier. And you can kind of think of the difference between these two as the one that's in the blue box, so the one that was originally on there, is that we're looking at the structure from the side, and so we can kind of see that 3D shape. And the one that I drew in green, we've kind of just flipped it over, and now we're looking at it from a top-down view. So we can't actually tell what's coming out at us because everything's just kind of flattened out. So on the test, if you draw it the way that I just did in green, it completely works. It's completely legit. It'll do the job. A little bit more on stereochemistry, and specifically stereoselectivity.
Professor, I have a quick question.
Yeah.
Where did the bond form from the diene to the one that is the bridge? Is it the double bond breaks and then those form to attach 5 and 6 attached to 1 and 4?
Yes. So we can draw our arrows going from 1 to 6, and then the pi bond to 4, and then that pi bond goes there. So that one and that one made the bonds between 1 and 6 and 4 and 5. Is that what you mean? Is that what you're asking?
Yes.
Okay.
Okay, thank you.
No problem. Any other questions on this slide? Okay. Sorry, I was moving stuff around so I can see if you guys unmute yourself. It's usually the easiest way I can tell if you're going to ask me a question. So this is showing essentially the same thing we saw on the last slide. The difference, though, is that we have these two groups that are now cis to each other. And when they are both cis, they're going to point in the same direction in our product. So again, we have that bridged product, and we have two different labels here, endo and exo. As you know, we like our labels in science. And when this structure forms, the substituents, so these are both aldehydes, but the substituents can either both point down or both point up. And the terms that we're using for these are in relation to the larger bridge. So because those aldehyde groups are attached on this side, we consider that carbon a 1-carbon bridge, and we consider this a 2-carbon bridge. So obviously 2 is bigger than 1. So that when we describe them as either being endo or exo, we're describing how close they are or their relation to that larger bridge. So the term endo tells us that it is syn to the larger bridge. So it's essentially pointing towards that larger bridge. And then exo means that it is anti to the larger bridge. Now, how I think about these and the way that makes sense in my brain is for exo, I think of exiting. And those substituents are pointing away from the ring. They are exiting the ring. That's what makes sense in my brain. And then for endo, I think of into. So that ring system is at an angle. And so the substituents are kind of pointing into, like that, if you think of the ring, that folded ring is like a bowl. They're like pointed into the bowl of the ring. So the into and the exiting is essentially what makes sense in my brain. Now, the big moral of the story, the most important thing on this slide is right here. The major product is going to be the endo product. The reason is because those endo substituents give a more favorable transition state. So I'm going to show you pictures of this transition state on the next slide. You don't have to draw this though, just giving you forewarning. This is not something I would ever ask you to draw, not because it's a complicated concept, but because it's a complicated drawing. This is not going to come out pretty. So we have the endo option on the top. We have the exo option on the bottom. The dashed lines are showing the new bonds forming. If our electron withdrawing group substituents are in that endo position, so they're essentially underneath the diene, then they can help pull the electrons through the structure and help stabilize that transition state because they are electron withdrawing. When they are in the exo position, they're too far away to help or to stabilize or to participate. And so it's not that they make things worse, it's just that they aren't there to stabilize anything. So in the endo position, they're helping to stabilize that transition state. So again, the most important thing on here though is that the endo is our major product, and our reasoning is because it stabilizes the transition state. Questions on that mechanism, transition state, any of that stereo stuff so far?
So we just need to know that endo is the more favored product and the exo is the minor.
Yep. Yep.
Got it. Thank you.
So a little bit of Regio Selectivity then, and then this will lead us into drawing some practice structures. If there's symmetry, there's only going to be one product. Because no matter if you match them up head to tails or tails to heads or heads to heads, whatever, match them up different ways, you're going to get the same product. If they're asymmetrical though, there's going to be two possible products. So let me show you where those two possible products are coming from in this example down here. So I'm going to number my structure like I have been doing. So we have our diene with a methoxy group attached and our dienophile with an aldehyde attached. And I'm going to get this product. Now, if I take that dienophile and I'm going to flip it over, because this is how we get our other product. And now I'm going to say 5, 6. 1, 2, 3, 4, 5, 6. So same reaction, same pieces. We've just matched them up going in one direction and then flipped that dienophile over and matched them up going in the other direction. Now, we do have a major and a minor product listed on here. This last bullet point tells us why. The major product is based off of resonance and partial charges. So what does that mean? So here's those same two products. We have our diene with our methoxy group attached, and we have our dienophile with our aldehyde attached. So with that diene, as it goes through the resonance, and this is our electron donating group. So we know it's an electron donating group because we have that lone pair attached to a heteroatom. And we can see it in the resonance. The electrons are being donated towards that pi bond. So what we end up with in that resonance contributor is a negative charge on one of those carbons. So this is the resonance hybrid that we make. So we have that partial negative charge on one of those carbons. And then on that dienophile, we have a electron withdrawing group, and we can guess that, assume that, figure that out, because we have a pi bond with a heteroatom. And again, we can see that right here. The electrons are going onto that oxygen, so they're being withdrawn from the rest of the molecule. You can always think of it in relation to the carbon. So they're being withdrawn from that carbon, or over on our diene, they're being donated towards that carbon. This is organic chemistry, so everything's focused on the carbon itself. And then we have one more arrow. And when we add in that second resonance arrow, then it creates a carbocation on that end carbon. And so the hybrid that we get for that structure puts a partial positive charge on that last carbon in the chain. And so let me do some numbering on these like the other ones. We're going to get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the methoxy and the aldehyde are opposites from one another in order to match up those partial charges. So the way that they're arranged is so the partial positive and the partial negative are next to each other. So it creates the most amount of attraction. The alternative then would be if you had two of the same charges, if you had two positives or two negatives. And so if that's the case, you would want to arrange them so that you would minimize repulsion. So we're always going to match them together so that we're either increasing attraction or decreasing the repulsion. So we are going to practice this. Let me draw something out here.
Hey, Professor.
Yeah.
So on the last slide, the methoxy and the aldehyde were oriented so that they were matched up. It's like being on the 2 and the 5. That's like what makes them matched up.
So what makes them matched up is that the positive, the partial positive, and the partial negative are going to form a bond.
Okay.
Does that make sense?
Yeah.
Okay. So here's our two starting materials. So we have our diene and our dienophile. And so we want to know what the products are for this. And we want to know just the major product. So in order to know the major product, we have to know some resonance to go along with this. So we're doing essentially the same thing that was on the last slides, but for a couple new products here, or new starting materials, excuse me. So we're going to start with our ketone. So is our ketone an electron donating or electron withdrawing group?
Would be withdrawing.
Good, it is withdrawing. And if you're ever in doubt, I'm going to draw one that I'm going to erase here in a second, but I will show you how to figure it out. So if you're trying to figure out if it's electron donating or electron withdrawing, think about what's going to happen if you do that. So that would be electron withdrawing because it's pulling the electrons away from the carbon. So if we do that, it's going to put a negative charge on the oxygen and a positive on the carbon. But if we went the other direction, if we did this, that would be electron donating, and it would put a positive on the oxygen and a negative on the carbon. So we know, because of electronegativities, patterns, and reactions, we know that that's just not going to happen. So you can kind of think of them in that way in terms of what makes sense with our bonding and our mechanism rules. Okay, so we know that this is an electron withdrawing group. So I'm going to start with my first arrow right there. Oh, that was a horrible bond. Let's try that again. So we get that. We're going to continue down that line. So I'm going to do this. I have a positive there. And then it looks like we need one more. So our resonance hybrid then is going to put a partial positive charge on that last carbon because of our resonance contributors. Now there are other positive charges in our other resonance contributors, but this last resonance contributor is going to be the most stable one with a charge, because the charges are farther apart from one another. And then in our dienophile, we have our electron donating group. So we're going to do the same thing. I'm going to do an arrow. And when we have an electron withdrawing group, we're usually showing one arrow at a time. But when we have an electron donating group, we're usually doing 2 arrows at a time, because I can't stop there. That would give carbon 5 bonds, and we can't do that. So we're going to take those pi electrons and put them right there. And so what we end up with is this. And so really, that tells us what we end up with is a partial negative charge up there. So I have my partial positive and my partial negative. The way that they're set up right now, we don't have the partial positive and the partial negative next to each other. So I'm going to redraw these. I'm going to just cut this in half a little bit here. Okay, I gotta fix that drawing. That was not good. And then for my dienophile, I need to flip it around. I'm going to put my NH2 on the top and my methyl on the bottom, because down here was my partial positive for my diene, and then the carbon that's farther away from that nitrogen group is my partial negative. So now we can match up that partial positive and partial negative to figure out our product. So I'm going to do some numbering. 1, 2, 3, 4, 5, 6. And we can show our mechanism arrows just to see how things are working. And I'm going to start at my pi bond between 5 and 6. I don't think I've started there yet. But for this one, it makes sense to start there, because carbon 5 is our partial negative and carbon 4 is our partial positive. So it would make sense that that starts the reaction, because that's where the strongest attraction is going to be. Now, once I get all my arrows in there, you wouldn't really know where I started, but I know where I started. All right. So I know I'm going to make a cyclohexane with a double bond in it. 1, 2, 3, 4, 5, 6. And then we just have some stuff to attach to it. So carbon number 1 has that methyl ketone attached. Carbon 6 has that NH2 group. Carbon 5 has the methyl group. So what about the stereochemistry on carbons 5 and 6? What should it look like? Both dashes, both wedges, one of each.
Would it be cis?
It would be cis. And so we could either draw it both as dashes or both as wedges. So I'm going to do wedges. So NH2 goes on carbon 6. My methyl goes on carbon 5. And then I'm even going to put the plus EN here because we would also get both dashes as our other product. Yeah, Nate.
Would that not just be a meso compound, or would it have to be symmetrical without the carbonyl at the top?
Yeah, so it's not going to count as a meso compound. It doesn't have enough symmetry in it. If they were both, okay, so if the carbonyl wasn't there, and if they were both nitrogens or both methyls, then it would be meso. But it doesn't quite have enough symmetry for it to fall into that category.
Great, thank you.
You're welcome. Any other questions on this one? Okay. Oh yeah, I had extra slides in there just in case. A little bit about MO diagrams. So we talked about the MO diagrams towards the beginning of this chapter, and really just kind of like labeling the parts of them. This is showing us the MO diagram of butadiene and ethylene. So really, the two smallest starting materials we could have in order to do a Diels-Alder reaction. In order to do the reaction, we have to take the electrons from one of them and put them into the orbital of the other one. Because remember, what we're creating in terms of a pi bond is we're only making one pi bond. And these MO diagrams are only showing the p orbitals. So they're only showing pi bonds. So this is talking about the formation of that. And normally the dienophile, so this one, let me label them. Normally the dienophile is our electron withdrawing group. And so because it's electron poor, it wants to accept electrons. And so when we do our donation, it can go in either direction, but the electrons in our highest energy occupied orbital, so the HOMO electrons from one of them, will overlap into the lowest energied unoccupied orbital, or the LUMO, of the other one. And it does say here, with the help of light, and it could actually be heat as well. Heat can actually make the reaction go in reverse though too, so light's more common. And then the last bullet point on here tells us that the MOs, the orbitals, have to be symmetrical in order for them to overlap. So this is what that means. And again, this is one of those pictures where it's good to know the concept. You definitely are not going to have to draw a picture like this, but it's really saying that they have to match. So meaning in cartoony picture world, that means blue matching to blue, red matching to red. What that means really though in the molecule world is that they're in the same phase. So we can think of this in a couple different ways. If we're thinking of electrons like particles, that means that we have to have a spin up and a spin down in order for them to get matched up properly. If we're thinking of electrons like waves, then when we match them up, they have to be in phase with each other, so going on that same wave. If instead we get this, that means they're out of phase. And so essentially that's the same thing as them repelling each other or canceling each other out, or it's the same thing as an antibond. So the colors have to match, they have to be in phase, they have to be symmetrical in order for that new bond to match up. Part of this does have to do with our example problem. So having those charges lined up in order to make the reaction occur. Looking at my notes, see what slide we're headed towards. Okay. So this is a kind of a heavy concept part right here, but it's not something we're spending a huge amount of time on because it does get in way over our heads for where we need to be. So big picture on this is that the orbitals have to be in the same phase in order for the bond to occur, is kind of the big picture idea there. Any questions on the MO diagram side of this reaction? All right, so that takes us into the fourth reaction. So remember way back a few slides ago where we started, there was 3 reactions on there. The first one was cycloaddition. So that's all we've done so far is the cycloaddition reaction. And then the next one on the list was electrocyclic. So this is the electrocyclic reaction. And I know there's a lot going on the slide, so let me try and simplify it. This right here is reaction number 4. This is the electrocyclic reaction. We can either start with 6 carbons or with 4 carbons. The change that happens with this reaction is that we're going to gain 1 sigma bond and we're going to lose 1 pi bond. So if we look at the reaction between the 6 carbons, this bond right here, I'm just going to, oh, that's not what I wanted to do. Here we go. I'm just going to kind of squiggle it, make it purple. That's the new sigma bond that formed. And then again, to see the pi bond that was lost, we're really just have to look at the overall count. So our original structure started with 3 bonds, 3 pi bonds, and now we only have 2 pi bonds. So there's a lot of similarities between this and the one we just looked at. There's 3 mechanism arrows, and we are doing that cyclic domino effect mechanism. And we are creating a 6-membered ring if we start with 6 carbons. The example right underneath it, again, that bond on the side here, that's our new sigma bond. And we went from 2 pi bonds down to just that 1 pi bond. Now, the book goes into a lot of detail on the stereochemistry for this. And I'm going to point out before I say the rest of this slide is that stereochemistry is not our focus for this reaction. In the past, I've taught it in a lot more detail than what we're going to do today, and it ends up being much more confusing than it needs to be, and students end up focusing a lot more on it than they should, because honestly, chapter 17 and 18 and the stuff we've already talked about in this chapter are way more important. So what we're going to say about stereochemistry is that we can create whichever stereochemistry we want. What I mean by that is if we look at the example in the middle, in the top example, the methyls are pointed out away from each other. And in the bottom example, they're pointed in the same direction. And whether we use heat or light, we can force them to go into either cis or trans. Because a lot to do with those MO diagrams. It has a lot to do with electrons flipping to different orbitals. And honestly, it goes way more into the physical chemistry side of things than we need to know. So big picture here is that we can force it to go into either stereochemistry option. How you will see this on the test, just so you know, because again, it's not a focus for us, but how you will see it is that it's going to be a multiple choice question. This and the next one we're going to look at. So what I mean by that is I will show you a reaction that looks, you know, like this middle one here, and then ask you, is it cycloaddition, electrocyclic, sigmatropic? So you need to be able to recognize this one and the next one. But they go very quickly from being too easy to too hard. It's hard to find middle ground on these, and there's not a lot of places we can take it afterwards, because I like to do kind of reactions in a chain, and this doesn't fall into that. Are there questions about this?
The two arrows that are kind of showing like one's larger than the other, is that saying it's like the major product?
Yeah, you mean in the part that's in the green box?
Yes.
Yes. So it's telling us that they're in equilibrium with each other, and then that bigger arrow is pointing to the one that would be in a higher concentration.
Okay, thank you.
You're welcome. Anything else on our electrocyclic reaction? Okay. So then the last reaction in this chapter is the sigmatropic reaction. And overall, there's no bond changes to this one, which sounds weird, because there is something that happens. But what we mean by that is the number of sigma bonds we start with and the number of pi bonds we start with is the same as what we end up with. So here is our reaction number 5 and the mechanism, and we have 2 pi bonds. We can see what's happening. So it's telling you that a sigma bond is breaking and a sigma bond is forming. So overall, the number of sigma bonds stays the same. So we can't really see a reaction is occurring unless there's a substituent. So on the bottom reaction here, let's see. 1, 2, 3, 4, 5. 5, 4, 3, 2, 1. So I kept that methyl group on carbon number 4, but you can see that the double bonds have just kind of shifted around that ring. So I'm sorry, it's not even a ring. They've shifted around that chain. So they've gone from carbons 2 and 3 and 4 and 5 to 1 and 2 and 3 and 4. The other thing that reaction on the bottom is emphasizing is that a hydrogen is being shifted from carbon 1 to carbon 5. So the bonds are moving around, but overall, overall the number of bonds haven't changed. There's a couple of specific examples too. So these are both still in that sigmatropic category. They're just specific ways to look at it. So the first one is a Cope rearrangement, and it is essentially just looking at a carbon chain, so having the alkenes move around. And then the second one is a Claisen rearrangement, and this is when there's an oxygen in the middle. So we go from having an allylic oxygen to a carbonyl. And you'll hear that name Claisen again. We do a Claisen reaction in a later chapter, and it does involve carbonyls. So these ones are a little bit easier to see that the reaction has occurred because there's something that makes it asymmetrical. So either that methyl substituent or that oxygen. And then just like the electrocyclic one, this one will be a multiple choice question that you essentially just have to identify it. Questions at all about this one?
When you mean by identify, do you mean identifying either the reaction or the name of the reaction?
The name of the reaction. So if I gave you this on the test and said, what reaction type is this? And your options were cycloaddition, electrocyclic, sigmatropic, knowing that that is a sigmatropic reaction.
Okay, thank you.
You're welcome.
Oh, sorry. Will we have to know the difference between the Cope and the Claisen reaction?
No.
Okay. Thank you.
Anything else on that one?
I didn't quite catch what I think it was Nola who asked the question. Are you saying that for this one we just need to identify it's a sigmatropic, or we need to be specific, like this one's Cope and then or this one's Claisen?
Just the sigmatropic part. You don't have to identify specifically that it's Cope or Claisen, because they would fall under the sigmatropic category.
Okay, thank you.
You're welcome. Anything else?
Yes, I have one more question.
Okay.
Instead of heat, could we have used light, or is this only specific for heat?
No, we could have used light for this one as well.
Okay, thank you.
Mm-hmm. Anything else on these ones? All right, so last topic in this chapter then is UV vis. So we have talked about 3 different types of instrumentation: IR, NMR, and mass spec. You guys have become pros at them with your test. UV vis is the 4th type, and we didn't include it in our test, and it doesn't get included in those first couple chapters, partly because it just has limited uses. So the idea works the same as NMR and IR. So NMR uses radio waves and IR uses infrared rays. UV spectroscopy uses ultraviolet and visible waves. You probably could have guessed from the name, but so that means that we're going to hit our molecule with a range of ultraviolet and visible wavelengths. They're going to absorb the energy if it's the right amount, and those electrons will jump to a higher level and then fall back down and release that energy. So when I say it has to be the right amount, so the example that's shown down here, this gap is representing the energy difference between the 2nd and the 3rd orbitals. So if the energy isn't high enough, it won't be enough energy to get the electron to that higher level, or if it's too much and it's in between levels, that's not going to help out either. So it does have to be the right amount, which sounds very specific, but that's why we hit it with that huge range of wavelengths, because they represent all of those different energy levels. What we're measuring is the light that is absorbed, and from that wavelength that is absorbed, we know the energy. And then from that, what this instrument tells us is if our molecule has conjugated pi bonds, and if it does, how many. So this one has very limited uses. This is what the graph looks like for it. So I kind of always laugh at this graph a little bit because it's so simple compared to some of our other ones, but it's showing us that we have a peak at 217. And so that's telling us that our molecule, yes, indeed, has conjugated double bonds. There's math that goes into this, looking at the intensity of the beams, and what we're getting from it, though, is the absorbance value that turns into lambda max, or the wavelength of the strongest absorption point. That lambda value, that wavelength value, is going to change based off of how many conjugated double bonds we have. So when we have 4 conjugated double bonds, our wavelength is larger than if we have 3, which is larger than we have 2. So as the number of pi bonds increases, the wavelength is increasing, and the reason for that is because the energy gap between the orbitals is actually decreasing. So remember, bigger wavelengths, so bigger distances between waves, means lower energy. And that is represented in the little graphs down here in these little mini MO diagrams. Looking, I think I said everything I wanted to for that. Yeah. We can calculate these values. So knowing, let me go back up a slide. If we run the instrumentation and we get a value of 290, we can do a couple things with that number depending on what we already know. So for example, if we thought that this was our structure, then we could do these calculations to essentially provide evidence to say that the value we got from the instrument matches the expected value from the calculations. If we get the value of 290 and our structure is just a complete unknown, then these of course are listed in tables, just like all of our other instrumentation values. And we could look up 290 to see what type of structures 290 is associated with. The calculation here is based off of how many double bonds are conjugated with each other, if there are substituents coming off of those double bonds, and then if those double bonds are part of a ring. So it's kind of just matching things up and doing some addition. We're not going to do the math behind this. What you need to know for this is this trend that's up here. So if I gave you 2 structures, you should be able to predict which one would have a larger wavelength, but we're not going to do the math. Last slide then for this is looking at a couple larger structures. So if our structure has enough double bonds in it that we are now in wavelengths that push us into the visible light, so we're in big enough wavelengths that we've moved into the visible light, then these are the ones that will be colored compounds. So beta carotene is what makes carrots orange. And so that means that the color that we're seeing is opposite from what it absorbs. So because we are seeing orange, that means that beta carotene is actually absorbing a wavelength in the blue category, within the blue range of wavelengths. And then the structure on the bottom there is lycopene, which is what makes tomatoes red. And because it's red, we know that it's actually absorbing wavelengths in the green range. And so then we're seeing that red color. So I always think this is interesting because the reason why these things are colored is because they have a bunch of double bonds. This isn't true for everything. We're talking about organic structures here. So there's a lot of metals that will make different compounds colored as well. So this is looking at just the organic molecules and what causes them to have different colors. So I know you guys didn't get to experience a whole lot of lab in the spring, but what we normally think of as organic chemistry lab is we're making white powders and kind of yellowy oils. And that's honestly kind of it. It's not usually a very colorful lab or a very pretty lab. So if it's not a field that people find interesting, then lab usually doesn't help them get interested in it. I my high school chemistry teacher told me that she loved chemistry because of how colorful it was, but she went into inorganic chemistry, which is all the metals, so it is much more colorful. Questions on the UV stuff?
So if a compound doesn't fall within that range, then it could just be colorless, basically.
Yeah, either colorless or like if it's a powder, just like a white powder. Yeah. So if it's a liquid, it would be colorless.
Are we going to get to chapter 17 today?
What time is it? Yep, we're going to start chapter 17. Because this is our last slide, and we still have 20 minutes left about. Any other UV questions? All right, I am going to switch over to chapter 17 then. But let's not start in the middle. Go up here. All right, so chapter 17. 17 and 18 definitely go together really well. They're somewhat of a continuation of chapter 16, but with a big focus on benzene. So chapter 17 is called Aromatic Compounds. So originally aromatic compounds were given that name because they smelled. Sometimes smelled good, sometimes smelled bad, but they smelled. That's definitely not how we categorize chemicals anymore, but the name stuck. So we use the word aromatic or arene, and those both generally mean that they contain benzene. We're going to expand on that aromatic definition though, and look at, well, I'll just leave it at that. We're going to expand on that definition. What they have in common, everything that gets that label, is that they are all very stable and very difficult to react. So we will do an entire chapter. Chapter 18 is all about benzene reactions, but what you'll see is that they all require some type of catalyst to help them out. The two structures on the bottom, the one on the left is cocaine, and the one on the right is acetaminophen. So this is just to show you that benzene shows up everywhere. So in things that are found naturally, in things that are manufactured. Because of its stability, we find it in pretty much all types of products, whether, again, if they are natural or made in a lab. This is a new structure for us. So I know we talk about benzene often, but we actually haven't had a chapter that's covered it. So we do have to talk about nomenclature. And I have the nomenclature broken down into a couple slides. The first one is talking about monosubstituted benzene. So monosubstituted. The naming is nice and easy because it's just whatever the substituent is and then benzene. So we have chlorobenzene, nitrobenzene, ethylbenzene. Nice and easy, but there's a twist. That bottom list is 8 names. These are common names. Now, normally, I don't have you memorize common names. I don't even usually care about them too much. Benzene is an exception to that. These common names are so common and used so much that we do need to use them and memorize them. So these 8 that are down here, memorize these. So flashcards, writing them out, whatever makes sense to you. So each of these are monosubstituted, and they have all have small substituents. So here's their names. Toluene is when we have this methyl group attached. Phenol is an alcohol. Anisole is a methoxy group. Aniline is an amino group. Benzoic acid is a carboxylic acid group. Benzaldehyde is an aldehyde group. Acetophenone is a methyl ketone. I don't know if we've really used that term, but it's a ketone just with a methyl on one side. And then styrene is this ethylene group attached. So memorize. All right, so we did monosubstituted. We need to talk about what happens if benzene itself is the substituent. So we're following the same rules that we've done before, meaning we're looking for the longest chain, and that becomes our parent. If the longest chain is 7 carbons or more, then that becomes our parent chain, and the benzene is a substituent. When benzene's a substituent, we call it a phenyl group. Now, because of that, because it's called a phenyl group, it can be abbreviated in a drawing as just a pH, or we can even abbreviate it as the Greek letter phi, which is nice when you are writing out notes, because it can be a nice quick way to draw a benzene attached to something. And I'm going to put one more example on here. Let's see. Okay, making sure I had enough carbons. So my parent chain, I believe, is 9 carbons if I counted right. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I have a benzene attached to it, but I also have this CH2 group. So when it's just a benzene attached to our ring, we call our chain, well, attached as a substituent, let's be a little generic there, we call it a phenyl group. When it also has a CH2 group there, we call it a benzyl group. So the name for this would be 5-benzyl-nonane. And we call it that because that is a benzyl carbon. When we have double bonds, we can talk about the carbons in the double bond as vinylic carbons, and then the ones right next to it are allylic. When we have a benzene ring, the ones right next to the ring are benzyl carbons, and then the ones in the ring are aryl carbons. So going along with that arene name. And so when we say benzyl, that's telling us that there's a benzyl carbon, and it can't be a benzyl carbon unless there's a benzene attached to it. So the term benzyl as a substituent is including that ring and that CH2 group. All right, what about
Should we also memorize? Sorry, should we also
go ahead.
memorize benzyl as well then?
Yeah, benzyl's one that you'll need as well. It doesn't come up as often, but it's a good one to know, especially knowing the difference between benzyl and phenyl. So we've talked about di-substituted because they came up as we were talking about the take-home test. But we can use ortho, meta, and para to describe those substituents. And remember, these can only be used. That is not how you spell only. Let's try that again. These can only be used with 2 substituents. If we have 1, it doesn't make sense. And if we have 3, it doesn't describe the relationship between 3 things. So it doesn't make sense or doesn't work. Each of these has 2 names already written out. So the middle one, for example, is meta-bromotoluene. So the other thing that these 3 structures have in common is that they all have one of those common names. So anisole, toluene, and benzaldehyde. And we have the ortho, meta, and para. And then underneath that, in parentheses, we have the name, but with a number instead. So if we are using one of the common names, then the substituent that's part of that common name will automatically be carbon number 1. So 1, 2, 3. So 3-bromo. Benzaldehyde, the carbon where the aldehyde is attached, is carbon 1, 2, 3, 4. There's one more way to name all of these. So we have the name, we have the number. The other way to do it would be just to put the letter. So M, bromo, toluene. And all 3 of those names tell you the same thing. They all work. They would all be correct on a test if I asked you to name that. All right, last one, and then we're gonna do some practice. Multi-substituted. And the first bullet point there just says same rules as always. So we're looking for the parent chain. We are numbering our chain. We're naming our substituents. We're putting our substituents in alphabetical order. We're using the lowest numbers possible. We've used these rules since we learned about alkanes. So we're going to do some practice. So if you have your book or the slides printed out maybe, you might want to have them open to the common names list. It's going to tell you what page it's on. Let's see if I can find it real quick here. It's in the very beginning of chapter 17, I know that. So on page 753, all of the common names are listed at the very bottom there. So we're just going to practice a few of these. I realized when I started doing my lecture earlier today with the other class that I put way too many examples on here to do in a reasonable amount of time. But the other class did ask that I post all of the answers for these so that you guys can practice them. So I will post that as a PDF probably tomorrow. So let's pick out, we're going to start with letter B. Using one of our new common names, what are we going to use as the parent name for this structure?
Would it be the phenol group because of the OH?
Mm-hmm. There's actually more than one option. So what is the other one that you see? Anybody?
Is that 4-chromo, or for A anyway, 4-chromotoluene?
4-chlorotoluene. Yeah, so A would be 4-chlorotoluene. That is correct. So for letter B, instead of phenol, what is the other? Oh, aniline. Thank you, Ural. So we could also use aniline because that would be the parent chain with our amino group. So the question that might be in your head and that I always get asked right here is, well, which one do we pick then? Which one has priority? And the answer is neither one. Because these are both common names, there isn't an IUPAC rule that says which one we should use or which one has priority. So it doesn't really matter. You could name it from either one. So we will do the enol one, or excuse me, the phenol one. I think I just combined their names into one. But we're going to do it with the phenol. And because that is what we're going to use, that means that this is carbon number 1. And then really I just have to decide if I'm going to go clockwise or counterclockwise. And usually it's pretty easy to tell because we're just going to go towards the closer substituent, because that will give it a smaller number. So I'm just going to go towards that bromine. So 3, 4, 5, and 6. What are we going to start with alphabetically? What comes first alphabetically in this name? Do we know what to call an NH2 group as a substituent?
Amide?
Amine?
You're both very close, but not quite.
Amino.
Amino, yeah. So it is an amine, but as a substituent, it's an amino. And amide is when we have a nitrogen next to a carbonyl. It's amazing what changing one letter does. So aminos definitely can come first alphabetically. So we're going to call this 5-amino 2-bromo phenol. Notice the difference in the pronunciation. Phenol phenyl. Their spelling, of course, is very similar. They sound very similar, but they're very different things. And if you are watching videos and, you know, doing practice problems, just want to make sure you're not going to get like an oral exam for me, so you don't have to know that based off of like what you're going to put on a test, but something good to know. Let's look at letter G up here. What is going to be our parent chain name for letter G? Good. Then, yeah, so we're going to use benzaldehyde for this one because we have that aldehyde group attached to it. So that's the common name for that then is benzaldehyde. And so as I number this around the ring, I'm going to do 1, 2, 3, 4, 5, 6. And I specifically picked this one because of that substituent on number 5. So what is the substituent on number 2 called? We'll start with the easy one there.
Ethyl.
And ethyl. All right, here's the tricky one. Let's see if we remember. What's the substituent on number 5 called?
Isopropyl.
It is an iso.
Isobutyl.
Isobutyl. So 1, 2, 3, 4. It has 4 carbons overall. Those last 2 methyl groups are in kind of that forked position. So that's why we give that iso title. Now, if you looked at that and forgot that, or maybe you had another teacher that did not tell you that and didn't use that term, the other way to name this is to treat that propyl group like the substituent, and then that extra methyl as a substituent on the substituent. So we could call this 2-methyl propyl. So both of those would definitely work. So let's put this all together in a name then. Alphabetically, we're going to start with the ethyl. So let's see, I'm going to go up here. 2-ethyl. Got to learn I can't go back and correct things. Just doesn't match up right. Okay, 2-ethyl, 5-isobutyl. Oh, I should have asked you guys this because it makes a difference. Did I alphabetize those correctly? Let's start there.
Yes.
Yeah, I did. So when we use isobutyl, what are we using to alphabetize it? The iso or the butyl?
The iso.
Yeah. So I think I even put this on the last slide. Yeah, so we ignore the prefixes except iso and cyclo. So those both count. So the ones that we're ignoring are sec, tert, or any number-based ones. So di, tri, tetra, so on. If we were using that methylpropyl naming version, we would alphabetize it based off of the M. So if you have a branched substituent, then you're just using whatever letter comes first. All right, so 2-ethyl, 5-isobutyl, benzaldehyde. All right, let's do one more. Let's do this one down here. Actually, let's not circle that because that's going to be in the way. Letter J. So we don't have a common parent name that works for this one. So our parent name would just be benzene. So should I start naming it at that chain or at that ring? Or do I even need to number it?
Ooh, you don't, because those are para.
They aren't para, but you're on the right track.
I'll get one of these.
Are they meta?
They are meta. So we're going to name it using numbers as well. So I'll show you how we would number it. But we can do meta. And then which substituent name is going to come first?
Cyclopentane.
Good. Cyclopentyl, ethyl, benzene. And so that's just one big long name. So meta cyclopentyl ethyl benzene. So that tells you that there's a benzene ring, there's an ethyl attached, there's a cyclopentyl attached, and they are meta to each other. Now, because that cyclopentyl comes first alphabetically, that's where we would start numbering it. So 1, 2, 3, 4, 5, 6. So if we did put this with numbers instead, we would say 1 cyclopentyl, 3 ethyl benzene. Any questions on that one? All right, so I think this is our, let me double, sorry, I'm skipping ahead here for a second. Okay. The structure of benzene was figured out by a guy, so I always say his last name is Kikule. I honestly don't know how to pronounce it though. I think it's German, but honestly, I should look it up, and I have not yet, so I should do that. The formula was figured out quite a while before that by Michael Faraday, so physicist, and they had tried to figure out how you can put 6 carbons and 6 hydrogens together and have it make sense. And the way that he figured it out is he had a dream about snakes biting their own tails. And that turned into the structure that we know today. So there's, of course, lots of ways to draw it. We have the 2 different versions of resonance. So either in the skeletal form or the Lewis structure. It's also very common just to see it with a circle in the middle. So essentially representing that resonance hybrid. We know that benzene is very, very stable. We can provide evidence for that because of the heat of hydrogenation. So based off of other alkenes, we would expect a heat of hydrogenation reaction to release 360 kilojoules of heat because it's about 120 per double bond. But in reality, it only releases 208 because it's so stable. So it's already at a low enough energy level that it's releasing a very, very small amount. And it doesn't react in the same way that just an isolated double bond does. So as I mentioned before, it does go through reactions. It just needs a lot of help. And then last slide of the day is looking at the MO diagram for benzene. So it looks different than the other ones we've talked about because benzene is in a ring and not a chain, but we have our bonding MOs, we have our anti-bonding MOs. The one that's lowest in possible energy here is showing that full overlap between all of those double bonds. And then as we move farther up in energy, we're getting less and less overlap. So we will use the MO diagrams to talk about a few other structures in this chapter. But again, the purpose of them is to help explain or help provide evidence for that stability. Yeah. So I will make a video for the rest of this chapter. So starting at section 5, and I will post that by Friday. And that will be our lecture for Monday. But that is it for today. So lab is asynchronous, of course, on Wednesdays. And on our schedule for today, we have the chapter 16 worksheet. And then I bet a lot of you didn't do the lab on Monday because you were working on your take-home test. So if you haven't done Monday's lab, make sure you're working on that as well. There's nothing due today, so you have time, hopefully, to work on those other 2 items. But that is it from me today. So I won't see you guys unless you come to office hours. I won't see you until next Wednesday.
Thank you.
Thank you.
Professor.
Thank you, Professor.
Thank you, guys.
Professor, I had a question.
Yeah.
For the nomenclature practice, letter G, I can't remember how to name it without using isobutyl. So if you were using the 2-methyl propyl.
So the way that, let's see, let me pull something else up just so I can draw it bigger. Where is my, oh, there it is. I just need to open up a new one. Okay, can you see my empty whiteboard?
Yeah, I can see it.
Okay. So, oops. So I don't remember actually what else was on that structure, but this is enough to get us there. So if we are naming it without using the common name, we start counting wherever it's attached to the parent chain. So the benzenes are parent chain. So that's carbon number 1, 2, and then 3. So this methyl group is a substituent off of carbon number 2. So essentially we can say there's a propyl group attached to our benzene ring, and then attached to that propyl group is this methyl group. So if we named this, we would, and actually let me just put something else on here so we can have something else there. But so this would be a meta. So we could say meta, and then in parentheses, 2-methyl propyl, close the parentheses, and then benzaldehyde. So we keep the entire name of the branch substituent in parentheses. So it's because we're saying that it's carbon number 2 of that propyl group.
Got it. Okay. Okay.
Does that make sense?
Yeah, that works.
Okay.
Okay. Thank you.
You're welcome.